This is math. This is Math 2020, and this is lecture 34. And in this lecture, we will cover I guess it's section 11.4, which is about the comparison theorem, which is another test for series. Okay, let's get started. Okay, it's the comparison test. There's actually two of them, so let's say comparison tests. And in this case, you have two series, summation A sub n and summation B sub n. And these have positive terms, so A sub n is greater than or equal to 0. Well, actually, I think probably positive, strictly positive is probably what we need to say. So greater than 0, and B sub n is greater than 0 for all n. So these are series with positive terms, and then the condition for the comparison test is that the condition is we will assume in what happens that A sub n is less than B sub n. Okay, so then the comparison the first comparison test is the following statement. It says that if the larger series, that would be the summation B sub n, and this could be less than or equal to, if summation B sub n converges, then summation A sub n converges. And the contrapositive is the other way the test is formulated. If summation A sub n does not converge, that is, it diverges, then summation B sub n, the larger series, diverges. So this is the test, and it's actually fairly simple to show why this is true. Here's the reason, or the proof. Let's just prove the initial statement. So let B equal the thing the series converges to. So then let S sub n be the nth partial sum. So k equals 1 to n of A sub k of the series A. We want to show that Sn, the limit of S sub n approaches a finite number. That's what it means for the series to converge. Well, clearly, since B is a sum of series of positive terms, and you're adding, B1 plus B2, etc. together, B is going to be greater than any partial sum of the A's. So let's let T sub n equal the sum B sub k equals 1 to n. So then it's clear that S sub n, which is greater than 0, is less than, I don't need to say it's greater than 0, is less than or equal to T sub n. And it's always less than, or T sub n is always less than or equal to T because you're adding more and more positive numbers. So S sub n for all n, Sn is less than or equal to T. And S sub n, since you're adding positive terms to at each point, S sub n is monotone. In fact, it's increasing. So it's bounded and monotone. So it's bounded and monotone to the sequence. So S sub n has a limit, a finite limit. So this comes from section 11.1 on sequences, and that's what we needed to show. So this is why the comparison test is true. Okay, so let's do some examples. That's my plan for the rest of the lecture. Okay, so here's an illustration. So let's consider, first of all, sum of 1 over n squared plus 1. N goes from 1 to infinity. Now, we think that 1 over n squared plus 1, we're staring at it, it behaves like 1 over n squared. And 1 over n squared, the series 1 over n squared converges. So maybe we can compare the two. And it is true that 1 over n squared plus 1 is less than or equal to 1 over n squared. And since summation 1 over n squared converges, that implies summation 1 over n squared plus 1 converges. Okay, so that's okay, that works. But now consider the following thing. Suppose I had some 1 over n squared minus 1. Now I can't start at 1 here because n squared, the denominator will vanish then. But let's start at n equals 2. So now the problem with this is I cannot compare this to 1 over n squared because 1 over n squared minus 1 is larger than 1 over n squared, not less than. So the test, the comparison test won't work in this case, won't apply here. So it won't apply. Okay, here's a case where it will, we can play the same game, and it will apply. N equals 2 to infinity 1 over the square root of n minus 1. So now 1 over the square root of n minus 1 is larger than 1 over the square root of n. And this, the smaller series, summation 1 over the square root of n, diverges. We saw that by, say, the integral test. This diverges. So therefore, this is the series here is going to diverge. So this will diverge. Okay, so these are just some examples. Let's continue. So now we get to some more interesting examples. So here's an example. Sum 1 over n squared plus n plus 1. I think this is example 4, if I'm not mistaken. So now 1 over n squared plus n plus 1 is going to be less than 1 over n squared, less than or equal to, for all n, bigger than or equal to 1, and summation 1 over n squared converges. So summation 1 over n squared plus n plus 1 converges by the comparison test. So you're giving a proof here. This is like you're giving a reason. And whenever you write a problem down in this type of business, you have to give a reason. I've given you the complete reason. How about the following example, example 5? How about the sum of ln of n over n? N goes from 1 to infinity. Now, we actually did this, I think, in lecture 33. Using the integral test. But you could also use the comparison test instead. See, 1 over n is smaller than or equal to ln of n over n, at least if n is at least e, because ln of e is 1 and then ln is increasing. And this is for all n. N bigger than or equal to e. Okay, so now summation, the series summation 1 over n, that's the harmonic series. This diverges. So therefore, the larger series, summation ln of n over n, also diverges by the comparison test. Okay. So now we had to deal with on a previous slide, we had to deal with this example 2. Example 2 was a problem. We couldn't figure out example 2 because we couldn't use the comparison test. Example 2, there's another comparison test which is actually more useful in situations like that. It's called the limit comparison test. And it goes like this. So you have series, summation a sub n, summation b sub n, and a sub n and b sub n are both at least 0 for all n. And so now we consider the following limit. The limit of a sub n over b sub n, this quotient as n goes to infinity. And this limit may or may not exist. So if c is a finite number, if the limit exists, if this limit exists and c is finite and c is at least 0, is strictly greater than 0, then summation a sub n converges if and only if summation b sub n converges. And likewise, it diverges if and only if the other one diverges. So this is an if and only if situation. So this is actually quite useful, as we'll see, in certain cases. In fact, let's go back to example 2. So return to example 2. So we have summation 1 over n squared minus 1. N goes from 2 to infinity. And what I'm going to do is I'm going to limit compare to summation 1 over n squared. So what I have to do is take a sub n over b sub n. That's 1 over n squared minus 1 over 1 over n squared. It doesn't matter which one you're calling a sub n, which one you're calling b sub n in this case, because you can reverse the test will work either way. Okay, so now this fraction can be rewritten as n squared over n squared minus 1. And as n goes to infinity, this tends to 1 as well, as is well known. So this is our c. C is positive. So therefore, summation 1 over n squared minus 1 converges since the 2 series, this is the 2 series up here in the right-hand corner, converges. So we've handled example 2. How about this example? I don't know which example number we're at this point. Let's see. Oops. We're at example 6. So example 6, oops. Example 6 is like this. I want to look at the sum n squared minus n over n cubed, oops, minus n plus 1. This looks like a complicated series. Well, here's the idea. We're going to do limit comparison, where n squared minus n over n cubed minus n plus 1 is compared with, limit compared with, see, the dominant term is n squared over n cubed, which is 1 over n. N squared over n. The dominant curve in the term in the numerator is n squared. That in the denominator is n cubed. And n squared over n cubed is 1 over n. So I'm going to compare this series with 1 over n, but I'm going to do a limit comparison test. So I have to take a sub n over b sub n. So that's n squared minus n over n cubed minus n plus 1. And then divide it by b sub n, but that's like multiplying by the reciprocal of b sub n. So that's n over 1. And this is going to give me n cubed minus n squared over n cubed minus n plus 1. Now what happens as n goes to infinity, the dominant terms matter, and this approaches the coefficient in front of the n cubes. and the quotient of the coefficient. So this is going to go to 1 over 1, which is 1. So that's our C. C is bigger than 0. So NQ, so this series, so the series n cubed minus n, n squared minus n, sorry, over n cubed minus n plus 1 diverges since summation 1 over n, the harmonic series, diverges. So these comparison tests are very powerful. But I should iterate or reiterate that the series have to be positive series. You cannot work with negative series with negative terms. Okay, let's do another example. Some of the examples get complicated. So here's an example. I think this is example 7. Summation 1 over n factorial. So I'm going to try this in 2 different ways. So the first method is kind of complicated. Here's the idea. 1 over n factorial should be less than 1 over n squared. N squared should be smaller than n factorial. So I'm going to put a question mark above that. Let me circle the question mark. So this is going to be true if and only if n squared is less than n factorial. And so we can ask why that's true, so whether that's true or not. So I'm going to put a question mark above that or below that. But you see, we can divide both sides by n. And if we divide both sides by n, we get the question whether the inequality n is less than n minus 1 factorial, because n factorial divided by n is n minus 1 factorial. Okay, well, that's good. And this is less than or equal to, we should be putting here. Okay, now having this, these are both integers. So this will be true if and only if the number n minus 1 is strictly less than n minus 1 factorial, right? Because if n is less than or equal, these are both integers. If you have one integer less than or equal to the other integer, then the integer on the left, one less, is strictly less than the other integer. So therefore, we get we ask whether this is true. But we could divide both sides by n minus 1 factorial, and we get 1, oops, is less than n minus 2 factorial. But now you could just check, n minus 2 factorial is easily determined but n minus 2 factorial, if n equals 2, 2 minus 2 factorial is 0, that's 1. If n equals 3, 3 minus 2 is 1. If n equals 4, or 4, 5, 6, etc., then this inequality is true. This inequality holds. And therefore, we can go backtrack and we recover the statement that 1 over n factorial is less than or equal to 1 over n squared if n is at least 4. And that's enough, right? So that's good. That's good enough. You can start, as long as n is finite, we just have to check that inequality. Now, to complete the argument, we use the comparison test. By the comparison test, summation 1 over n factorial converges since the two series, that is 1 over summation 1 over n squared, converges. And therefore, this is going to converge. Okay, so that's one way to do the problem. It's not the only way to do the problem. I'm going to try to do this in a slightly different way now. So here's an alternative solution. So here's an alternative solution to example 7. So the idea is this. Okay, I'm going to compare. Um, I'm going to do this in two steps. So I'm going to compare. I'm going to look at 1 over n factorial. And notice that that's 1 over n times n minus 1 times n minus 2, etc. So this is a product of polynomials, of linear polynomials in n. And so, this should be compared with, we're going to compare this with, in the limit comparison sense, there are how many factors of n are on the bottom? There are n factors of n. So I'm going to compare this with 1 over n to the n. Okay, but I'm going to do a limit comparison. Okay, so in other words, I have to take, if this is a sub n and this is b sub n, I want to take a sub n over b sub n. That's going to be 1 over n factorial times the reciprocal of b sub n, which is n to the n. So that's n to the n over n factorial. And again, this is like n to the n on top, and this polynomial here that you get for n factorial is like the highest power of n that occurs is n to the n. And then there's going to be an addition of lower order junk or stuff, not really junk, but stuff. Now, what happens when n goes, what you can do is by how we deal with limits like this, if we divide top and bottom by n to the nth power, this becomes 1 over 1 plus something that's at least over n. Okay, because the lower order stuff is powers of n that are less than n to the n. So this stuff is going to go away. This is going to go to 0, and this tends to 1, which is our c. Okay, so therefore, so by the limit comparison test, so summation 1 over n factorial converges if and only if summation 1 over n to the n converges. But now we know that summation, we can compare 1 over n to the n with 1 over n squared. It's easily seen that if n is at least, 2, this inequality holds. So this is the 2 series on the right side. And therefore, so that'll imply by the ordinary comparison test that 1 over n to the n converges. So that's another way to do the problem. I think the first way is easier, though. Okay, so that's all for today. We will continue next time with another test. So we're halfway through the chapter.